This is AP Calculus, section 6.1, page 3. Today we're moving on to differential equations and slope fields. A slope field is a graphical drawing of a solution to a differential equation. And a differential equation is just an equation that contains derivatives. And this slope field, shows segments of slopes of tangent lines at selected points. We're going to use this idea then to create a slope field. So again, we're going to show segments of slopes of tangent lines at selected points. So let's come down here to this example, and we have some differential equation right here, dy dx equals x squared. We've dealt with things like this before. We just didn't call it a differential equation, and we didn't do slope fields with it. But you have seen something like this before. We're going to make a t-chart here. We're going to look at some selected points, and we're going to figure out then what dy dx is. So let's just start at the point 0, 0. So at this point 0, 0 right here, we plug in to dy dx for the x coordinate squared. 0 squared is 0. So I'll come to that point 0, 0, and we'll draw a little baby segment there of a slope of 0. Choosing another point, how about the point 0, 1? Again, plugging into here, takes the x coordinate, squares it, so that's another 0 slope, horizontal tangent segment right here. Try another point, say 0, 2. Same thing, takes the x coordinate, squares it, so that's another horizontal segment there. And we see now that at any point 0, y, so any y value, dy dx is 0. This particular differential equation and slope field is only dependent upon the x coordinate. Y coordinate doesn't matter in here. So if I look at 1, anything, that slope will be 1. So if we grab a straight edge and look at 1, anything, slope is 1. So I'm going to take my ruler, my straight edge, and line it up along some points. If we were to draw a whole line of slope of 1, this is what it would be. But we only want a little baby tangent segment, so just that much. Then I'm going to take my ruler, and everywhere where x is 1, I'm just going to line up along these dots and draw a slope of 1. Anywhere where x is 2, so 2, anything, that slope is 4. So again, using the dots here to draw this slope of 4, if we choose this point right down here, and a slope of 4 would be up 4 and over 1. So I'll use my ruler to kind of connect those, and there's a segment that has a slope of 4. And following that concept as we move along these dots, each time I'm keeping my ruler lined up slope of 4. 1, 2, 3, 4 over 1. Once I run out of dots, then I can just do backwards, down 4, and to the left 1, etc. At x is 3, slope's 9. That's a tough slope to draw because it's so steep. If I use this point right here, up 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, I'm going to have to estimate over 1, so right there. A slope of 9 is a very steep slope, nearly vertical. I don't have enough dots there to continue, so if I just keep my ruler edge lined up with that one to keep the parallels going. See how my ruler is parallel with these previous slope segments? There we go. Looking at some negatives, when x is -1, slope is +1. Oh, so we can use those dots again. Line up for a slope of 1. Everywhere where x is -1, the slope will be a +1. You should be doing this with me. And when x is -2, slope is 4. 1, 2, 3, 4 over 1. And again, using those dots to keep that slope. And last row that our last column that we're going to do is when x is -3, that slope is 9. And there we go. There's your slope field. All right, when you look at this, hopefully you can see general concept or general trend of the slopes is they're very steep out here, and as we go closer to the y-axis, that slope turns, it flattens off, and then it turns steep again. So steep slope, flattening off, and turning steep again. We're seeing a curve, and I'm kind of following those slopes, flattening off. Sometimes I hit an actual little tangent segment, sometimes I go between them, but regardless of where I am, I'm kind of following the direction of those slopes. And when I sketch that curve in there, that one single curve is called a particular solution. That's one of them. There might be another one maybe down here. Maybe it comes through this way. There's another particular solution. And what we see, the general trend of the slopes here, what we see is the original function. What it was before we took a derivative. What shape is that curve? That's an x cubed curve, and that makes sense because if we had a y equals x cubed, and we did a derivative of that, that would give us a 1/3, x squared, and that is an x squared. Clearly this has an extra multiplication in here, a vertical compression, but same concept going on here. And this original function is the solution to that differential equation. when you look at these two particular solutions, you should see that they are virtually the same curve. They just differ by a vertical shift. So a slope field creates or shows a family of functions that differ by that plus c, or the vertical shift. All right. This particular differential equation was only dependent on x. It didn't matter what the y coordinate was. On page 4, we will look at a differential equation that is dependent on both x and y.